Hello everyone, in this video you will learn how to create a fluid simulation on curve-based grid, and based on this technique I have created two presets that allow to do fluid simulation on any size rectangular grid, curve or any mesh surface types like closed, open, quad or triangle with a lot of controls and features. More about them in the end of this video. So before we start, you first check out the tutorial by Singh about 2D fluid simulation on a square grid using the geometry nodes. If you follow his tutorial, you will get this kind of setup. This setup do the fluid simulation on a square grid. And if you want to understand the concept and the physics behind this fluid simulation, check out this web page by Jamin Wong, and he has explained the fluid simulation as well as the equations that are involved in the fluid simulation. Based on this web page, we're going to do some corrections to this setup. And for this, we're going to use Blender 3.6 geometry nodes simulation build on April 6. And this build has a cache system, means it's going to cache the simulation inside the Blender file. So there are two main steps we're going to follow in this video. In the first step, we're going to correct this setup based on that web page and also modify this setup, and that modification will increase the speed of this setup a lot, about 80%. And in the second step, we're going to create the grid based on the curve, and then we will do the changes according to that in this setup. So in this setup, this first is the settings for the grid as well as storing the neighbor coordinates. And in this panel, we are initializing the input parameters like velocity, divergence, pressure, and the color of the grid, or you can say the fluid. These two nodes are not that important. These four nodes are basically solving the fluid equations. And here in these two nodes, we are setting the velocity and color from the collider object. And in this, we are advecting the velocity. Here we are calculating the divergence, and then we calculating the pressure, and then we subtract the pressure gradient from the velocity, and then we use that velocity to advect the color. So this setup is for the incompressible fluid or like water. So density is not changing in this setup. So the first correction we're going to do is that we're going to change these two assumptions. The epsilon is 1 and the dt is 1. Epsilon is the grid step. From this vertices to this vertices is the grid step, and the dt is the time step. So that is assumed 1 in this setup, but we're going to change the equations or the group nodes to include these two parameters so that we can easily control the fluid simulation. The time step allow you to control the speed of the simulation, and that is similar that we have in the particle system. If we go to the physics and then the integration, we have this time step. So that's why these two parameters are important. So if we go to that web page, so on this web page, if we go down for the equations, so here, so d is the divergence and p is the pressure and u is the velocity, and here rho is the density, epsilon is the grid step, and delta t is the time step. If we use those parameters, the grid step and the time step, we have to also include these factors inside the divergence as well as in the pressure gradient term. So let's first add the grid step. Go inside this group node, add a reroute here, and this is the grid step. We're going to move this outside from this group node. Let's delete that, add the named attribute node, and then plug that into this and type here grid step, and also delete this value input. Now we have this grid step, and we can move this outside from this grid settings. So this is now independent from this, and here we're going to store that grid step. Now this is our grid setting, and this node is basically storing the neighbor coordinates. And here we're going to store our this dt or the time step. For the time being, I'm using 1, but we can change that later. Okay. Now let's change the heading. So now only assumption is the density is 1. Now let's do the changes inside these 5 group nodes as well as in these 2 nodes. Okay, so in this case we are calculating the velocity of the collider object. And if you remember the expression for the velocity from your high school, the velocity is equal to dx over dt. So this is displacement over dt. So to get the velocity from the displacement, we have to divide that by the time step. So let's divide this, then plug that into this true socket, and here we're going to use a different time step. This can be same for the time step that we used for this simulation. For the time being, we're going to use 0.5. Now let's go outside this, and if we go inside this is fine. We don't need to change anything here. Now let's go to this advect velocity. Here you can see that this velocity is subtracted from the position or the position vector. But again, if we want the position from the velocity, we have to multiply this velocity by the time step or scale this velocity by that time step. So now we are using this scaled velocity based on the time step. So that is the correct form for the position. Here we're going to also change that. Change this to scale and type here named attribute node and select the time step. Okay. Now we have changed the advect velocity as well as the advect color. But we're going to correct the expression for this divergence as well as for the pressure gradient. See, in this setup, we are calculating the velocity difference along the x-axis for the right and left neighbors. Along the y-axis, we are calculating from the up and down neighbor, and this is fine. And after that, they are added together and then used as average for the divergence. But that is not correct. If we go to that web page, here see the divergence equal to the is a velocity difference along the x-axis and plus the velocity difference along the y-axis, and that is multiplied by this factor, that is 2 epsilon is the grid step divided by the delta t. Our rho is 1 or the density is 1. So let's go to this and here we're going to change this to multiply, and basically here we're going to add that factor. So now we have this correct factor which is being multiplied to these differences, and that is the divergence. We don't need to include the negative sign because that we're going to take care in the calculate pressure node. So we have corrected this divergence and now corrected this the pressure gradient expression. Again, here we are not including that factor. If we go to that web page, this pressure gradient, this is the gradient, pressure gradient, which is subtracted from the velocity. So it has this factor, time step divided by the 2 times grid step. So we have to include that here. So basically we're going to use the scale node. So scale node is like multiplying each component of this vector by this value. Okay. Now we have added this correct factor for the subtract gradient expression, and if we play the simulation, see we have this. It is working, but there is a problem that is happening because of the incorrect form in this store neighbor coordinate group node as well as in the calculate pressure node. So what is the problem? So basically the current setup is calculating the pressure based on the neighbor coordinates. Means if we are at this grid point, the pressure is calculated here, here, here and here. And if we go to this web page, the pressure should be calculated at the next neighbor. See this I plus 2 and I minus 2 means we are not the neighbor grid point, but we are at the next neighbor grid points. So it's like we have to calculate the pressure here, here, here and here. So we are going for 2 steps for the grid. For that we have to store these next neighbor coordinates, and then we going to use that here. So let's go outside and go to this store neighbor coordinate node, and here we are storing these neighbor coordinates, this right, left, up and down. Let's duplicate this one, then plug this to this and this to the group output node, and let's duplicate this one and type here 2, because we are going for the 2 grid steps. This is 1 and this is 2. And now we have these next neighbors. Now let's rename this as let's use these coordinates to calculate the pressure. So if we go to this calculate pressure, here we have to use the next right. So this node is basically sampling the pressure at this location. It is using the sample nearest and sample index node. Okay, so type here next. So now let's see that. See, it is working fine, so there is no problem. And let me go to this side and let's check the speed. So because of recording this is higher, but before the recording it was around 80 millisecond, and currently it is around 179 millisecond. Okay, now we're going to modify some of the group nodes to speed up this setup, and that will increase the speed around 80%. Okay, let's go to this calculate pressure node and then this. So here we are calculating the index of that neighbor as well as the next neighbor points, and we don't need to do that inside the simulation. We can do that outside the simulation and it will increase the speed of this setup. Let's first store the index and then we will change this a node in the sample pressure at position and sample velocity at position. And here we're going to store the index. See, we are storing the position of the neighbor and next neighbor points, but we're going to store the index. So change this to integer and add the sample nearest node to get the index at this position, and then plug that into this node. Now we have the index of this neighbor points. Now let's go to the calculate pressure node, and inside this node we're going to use that index. So let's delete these nodes and change this to integer, and here we're going to use the evaluate node, evaluate at index. Plug that into this, and now we have the sampling of the pressure at the neighbor index. And same we're going to do that inside this calculate divergence. Go to this sample velocity position group node, delete these nodes, change this to integer and type here evaluate at index node, and then connect this to this index and then plug that into this vector. So now we have changed that into the index. Now let's check the speed. See the difference. Let me refresh this cache. The lowest value while recording is around 30 millisecond, and before the recording it is around 13 millisecond. So see the difference. It is huge increase in the speed. So now you have completed the first step. So this setup is corrected as well as is faster. In the second step, we're going to create the grid based on the curve, and then we're going to create the local space, and after that we will make the changes inside this setup to run the fluid simulation on the curve based mesh or the grid. So let's move this to the side and let's disconnect that, and then we're going to add the curve, and let's bring that curve here, change that to relative, and here we're going to add the resample node, change that to length, and then we're going to add the curve to mesh node. For the profile we're going to use the curve line. You can use any profile for this. So let's view this. So now we have this grid, and let's make a group node for this. Control G, and we're going to use the same length for the profile as well as for that base curve. After this node we're going to use the transform geometry node so that we can control the radius of this profile. So this is like the radius of this grid. So let's rename these inputs, change this to radius, and also change this to a float. By default it is around 0.25, it can't be negative. Go to outside this, so we have this grid. Let's rename this as static ks. So why I use this static sign? Generally I use convention for the group nodes that are internal for the setups. Means I don't want to accidentally change them for other purpose. That's why I use the static signs in my setup. So we have this. Now we're going to create the local space. So what is the local space and why do we need that? So let me first select this grid, and let's decrease this to 20, maybe even 10. So here you can see that these grid lines are perfectly aligned along the x-axis and the global y-axis. So there is no problem while using the global axis in solving the fluid equations, because these lines are perfectly aligned with the global axis. So however, if we go for this curve grid mesh, and we can see that these lines are not aligned with the global axis. So let me pick this point, and here we can say these lines are along this side and this is along this side. They are at different angles. So we're going to create this local space. We're going to call this as x-axis, which is along the length of this input curve, and perpendicular to the curve is the y-axis or local y-axis. And we're going to solve the fluid equations in the local space, not in the global space. Let's increase the number of this resolution of this so that we have this smooth grid. Now let's go inside this curve grid mesh node. Here we're going to create the local space for this grid. So before we go further, you should download my free presets, these fall off nodes as well as the utility nodes, and the link is in the video description. And in this case we're going to use this vector viewer node, and this node will allow you to view the vectors inside the viewport. So let's add the position. So we are seeing the position vectors and they are pointing away from this global center. And you can also use the axis colors. See the vector, they are along the x-axis are red, they on the vectors they are along the y-axis are green, and the rest of the vectors are changing their color accordingly. So this node is very useful, so you can download from the link which is in the video description. So we're going to use the curve tangents as our x-axis or local axis. So let's store them before this curve to mesh node, change that to vector, type here C tangent, and here we're going to add the curve tangent node. Now let's view them, type here C tangent, and see we have this. So this is our local x-axis, and so let's store that as local x-axis, local x-axis, and to get the y-axis we're going to use the normal of this grid mesh as well as these tangents to calculate this local y-axis. So let's add the normal node. So this is the normal of this grid, and then we're going to do the cross product with the local x-axis to get the local y-axis. Normalize this and then connect that to this node so that we can see them. So these are the local y-axis. Let's move these nodes to this side and let's store that as local y-axis, and we can also store the normal as our local z-axis, even though we don't need this. So now we have this local space, so let's add a frame for this. So this is our local space. So we have local x-axis, local y-axis, and local z-axis. I have tried different method as well using the normal of this curve, but if you add the tilt, and that will not work. So this is the best method using the curve tangent as well as the normal of this grid. Let's also store the grid step for this curve grid. So our grid step is basically the length step that we used to sample the curve. So type here the grid step. So now this node is completed. Now let's plug that into this, and let's go to this and connect that to the group output node. So let's increase the number of divisions of this grid. So we have this. It is running, but it is not accurate because we have to use the local axis. In the first thing, we're going to remove the wrap conditions. So this wrap condition is only for that square grid, is not for this curve grid. So for the time being, let's remove this, and we're going to do this fluid simulation without that wrap condition or wrap boundary condition. So let's go outside this and also delete the wrap condition from this advect velocity node and also from this advect color group node. So now we have that without the wrap condition. See, we have this problem because we haven't used our local space. So here you can see that we are using the global x-axis and y-axis to calculate the neighbor left, right, up and down points, as well as next, right, left, up and down points. Here we're going to use our local x-axis and y-axis to calculate the neighbor and next neighbors. Let's delete them. So for that we're going to use the vector scale node. Vector scale node, connect this to the scale, and for the vector we're going to use the named attribute node, and here we're going to type the local x-axis. Duplicate this one and connect this to the negative scale or negative grid step. So this is our local right and local left. Then duplicate these three nodes and type here the local y. So this is our local up and local down, and same thing we will do for the next neighbors. Let's duplicate this setup, connect this to 2 times grid step, then use this as our next right, next left, then next up and down. Okay, this is the setup, and inside this node we have removed the wrap vector node. So we are done with this node. Let's type here asterisk yes underscore. So now we're going to correct the calculate divergence and the subtract pressure gradient node. So we don't need to change the advect velocity as well as the advect color and calculate pressure, because pressure is isotropic and basically added from the next neighbor points, so we don't need to change that here. Here we are calculating the difference in the x component of the velocity for right and left points, and difference in the y component of the velocity for up and down points. These are for the global axis. We have to do that for the local axis. So for that we're going to use the dot product. Let me first add the dot product, then I will explain what it is doing. Let's add the named attribute, and here we're going to type the local x-axis. So the dot product is basically giving the portion of the velocity that is pointing in the local x-axis. Let's delete these two nodes, and here we're going to use this for this velocity or the left point velocity, and then we're going to use this for the subtract math node. And let's also delete these two and duplicate this one, and let's move this to the down. So this is going to be the y or local y, and here we're going to use this up velocity and the down velocity, and then use this for the subtract. So now we are calculating the divergence based on our local space from the velocity, and then we're going to correct this subtract pressure gradient. Let me move this to this side, and here you can see that we are using this the local x-axis and y-axis. So we have to repeat a similar step here. So let's delete this, and we're going to use the vector scale node. Use this as a scale, and for the direction we're going to use our local x-axis and duplicate these two nodes, and let's connect this as our scale, and for this we're going to use the local y, and then we're going to add these together. So now we have this pressure gradient in the local space, and then plug that into this scale node. So this is the changes. So let's rename these nodes. So now we have corrected the expressions for our curve base grid. So now you have completed the second step. So you have this fluid simulation on the curve base grid. And for the wrap condition, I'll show you the setup, which is very easy to do that. So to implement the wrap boundary condition, basically you have to wrap the right side point to the left side and the up points to the downside and vice versa. So for that, first you have to create the mask based on this end selections of the input curve as well as for the profile, because we only want to do the wrap conditions for these outer edge points. And then I calculate the vector that basically move this point to this side and the up point to the downside, and same for the left side to the right side and down point to the upside. And that vector can be calculated by just subtracting this position from this position, and same for the up and down case. So that is being done here. So let me zoom this. So this is wrapping left at right side and wrapping right side at the left side, and same for this top and bottom. And here I just add these vectors and also add this mask. So this is the mask, and these are the wrap vectors. So I have also created this inward vector so that we're going to only wrap the points whose velocity is pointing inside the grid. So the first condition we're going to do this in the store neighbor coordinate node. Here just add the wrap vector to the offset position and you are done here. And then in the add vector velocity, again you're going to add that wrap vector to this offset position and we're going to use this condition. And same I have done for this color, add vector color. If you do that, you will have this kind of a result. See, the color is being wrapped from up to down and it will be wrapped from this left side to the right side. So, and if you want to use the force, you can use that force here. Just add that into this and also multiply the force by this time steps to get the velocity from the force, because force is acceleration. This is it about the curve grid fluid simulations. Now I'll show you the presets that I have made based on this technique. So first is the fluid simulator for the grid curve, and it will do the fluid simulation based on the grid as well as for the grid based on the curve. So when you download this, you will get this file and it has two velocity influencers and then you have forces, this 7 forces group node, and then you have this main node that is a fluid simulator for the grid curve, and you will also get this particle add vector node. I briefly explained the settings of this fluid simulator. Now I briefly explain the settings of this fluid simulators. For more details, check out the tooltips as well as the documentations that come with this fluid simulator. Okay. The first section is for the grid or curve settings. You have these grid settings and these settings for the curve based grid. And here you can also define the profile for that grid, means you can use the custom profile or you can use the default profile, that is line or circle. And you can also offset these profiles as well as their angle. And this option is to show the input geometry that is being used for the fluid simulation. And this node also generate the UV map for this grid, and you can change its type based on with this option. And then you have this section that is the initialization settings. So here you're going to define the start or end frame of the simulation, time step, number of iterations to calculate the pressure, and then you have this section for the boundary conditions. So you have three types of boundaries, open, closed, and in the closed you have wrap and solid boundary. You can also enable them individually for the x-axis as well as for the local y-axis. And here you will define the color as well as the initial velocity for the fluid. And then you have these dynamic settings. This first section is for the internal dynamic settings and the last is for the external dynamic settings. In the internal dynamic settings, you have this dam factor. This is like the viscosity of the fluid. Then you have this upper limit on the velocity so that your fluid remain stable. And this is the iteration to smooth the velocity of this fluid. And this is really useful when your curve has very sharp edges. And then you have this option to confine the vorticity in the fluid. So when we run the fluid simulations, we have the vortices that are formed inside this fluid simulation. And this option is try to confine those vortices inside the fluid, because we are solving these equations numerically and it has dissipations. So these vortices may dissipate after some time. So this option is try to confine them in the fluid and make the fluid more turbulent. And then you have this option is the color fadeness. It will fade the color of this fluid into this fade color. These are the external dynamic settings, and here you can reset the color as well as the velocity of the fluid based on the selections, and you can also define the modes for the color. And this setting is to add the force to the fluid based on these force group nodes, or you can also define your custom force node to affect the fluid based on this selection. And this section is for the particle add vector. and this node is going to advect the particle based on the fluid motions of this grid. See, these points are moving based on the motion of the fluid. And here you have these initial settings like project the particles on this fluid grid, as well as wrap the particles using wrap boundary conditions. And then you have this initial color for the particles, dynamic settings for the particles. Here you can define the diam factor for the particle as well as the color. And this is very powerful because most of the inputs are based on the fields, and you can define your custom mask as custom nodes control this fluid. Now I'll show you the next preset, that is the fluid simulator for the mesh. So this is the fluid simulator for the mesh. It can run the fluid simulation on any mesh type, means mesh can be open, closed, or has quads or triangles. In this case you will also get this velocity influencers as well as these forces, and then you have this fluid simulator node, and you have this particle advector for the mesh case. Again, I keep the settings same for the both these simulators. You have this initial settings, then you have these dynamic settings are internal as well as externals. So in the initial settings, these are the same, but you have this a new setting, that is enable exact pressure calculations. So you have option to calculate the pressure approximately or use the exact expressions. The approximate pressure calculation is run faster as compared to the exact pressure calculations. In this case, you can define the boundary of the mesh based on the attribute. That can be done using the attributes in the edit mode. Just create the boolean attribute on the edge and then select the edges that you want to mark as boundary, and then go to the mesh and then set that attribute true. So the rest of the settings are same to the previous simulators. These presets are available on the Blender Market as well as on my Gumroad page. The link is in the video description. This is it, and if you like this work, then please do support me. You can support me by liking this video and subscribing to my channel, or you can buy my presets, or you can support me on my Patreon page. Until next time, happy noding, bye.